Picture two people. One is falling into a black hole, one is watching from a safe distance. From the watcher's perspective, the falling person slows down as they approach the black hole, reddens, dims, and eventually freezes in place just above the surface. Never quite crossing, they will appear to hang there forever. From the falling person's perspective, they cross the threshold smoothly, nothing dramatic happens at the boundary, and they continue falling inward. Both perspectives are internally consistent. Both follow from the same equations. Neither observer is wrong. This is what general relativity actually says about black holes. Not a dramatic wall of destruction at the edge, a place where time itself breaks down in completely different ways depending on where you are standing. Before we get to the black hole, we need the concept that makes this possible: gravitational time dilation. Einstein's general relativity says that gravity is not a force, it is the curvature of space-time caused by mass. And one of the consequences of that curvature is that time passes more slowly and stronger gravitational fields. A clock sitting on the surface of the Earth ticks very slightly slower than an identical clock in orbit because the surface clock is deeper in Earth's gravitational field. This is not a theoretical curiosity. GPS satellites orbit at an altitude where Earth's gravity is weaker, so their onboard atomic clocks tick faster than clocks on the ground. Engineers account for this with a correction of about 45 microseconds per day from the gravitational effect alone. Without the correction, GPS would accumulate errors of roughly 15 meters per day from gravity alone. Gravitational time dilation is an engineering problem that gets solved every day. The effect scales with the strength of the gravitational field. On Earth's surface, the difference is tiny but measurable. An atomic clock at sea level runs slightly slower than one on a mountain, because the mountain clock is slightly farther from Earth's center and thus in a slightly weaker gravitational field. The clocks at the National Institute of Standards and Technology have measured this altitude effect over a height difference of just 33 centimeters. A clock 33 centimeters higher than another ticks measurably faster. Time runs faster at the top of a room than at the bottom. The difference is small, but it is real. The closer you are to a massive object, the slower your clocks run relative to someone farther away. Now take that to an extreme. Make the object so dense that its gravitational field becomes so strong that time, as measured from outside, slows to a halt at its surface. That extreme is a black hole. A black hole forms when enough mass is compressed into a small enough region that its escape velocity exceeds the speed of light. Escape velocity is the speed you need to reach to break free of a gravitational field. Earth's escape velocity is about 11 kilometers per second. The Sun's is about 617 kilometers per second. If you compress the Earth down to the size of a marble, roughly 9 millimeters, its escape velocity would reach the speed of light. You would have a black hole. The Sun would become a black hole at a radius of about 3 kilometers. This critical radius is called the Schwarzschild radius, named after Carl Schwarzschild, who derived it from Einstein's general relativity in 1916 while serving on the Eastern Front in World War I. He sent his calculations to Einstein from the trenches. He died 5 months later of an illness contracted at the front. Einstein presented Schwarzschild's paper to the Prussian Academy posthumously. The Schwarzschild radius defines the event horizon, the spherical boundary around the black hole's singularity. The event horizon is not a surface in the normal sense. It is not made of anything. There is no wall, no membrane, no barrier you would feel as you crossed it. It is purely a boundary defined by the laws of physics, the point at which the escape velocity equals the speed of light. Cross inward, and no signal, no light, no information of any kind can ever come back out. Cross outward, and the black hole's gravity cannot hold you. From outside the black hole, watching someone fall in, you see them slow as they approach the horizon. The light they emit becomes stretched toward longer wavelengths, shifting from visible light toward red, then infrared, then radio waves, growing dimmer as the photons become fewer and more spread out. The falling person appears to decelerate, freeze, fade. They will never, from your frame of reference, actually cross. The mathematics of general relativity says the light from that final approach takes infinitely long to reach you. But this is an effect of how light travels through curved spacetime, not what the falling person actually experiences. From inside the falling person's frame, time proceeds normally. The horizon is not an observable location as you approach it. You do not feel it, see it, or encounter any physical barrier. In a large enough black hole, you cross the event horizon without noticing anything unusual. What happens next is where it gets strange. Once inside the event horizon, the singularity is in your future in the same unavoidable way that tomorrow afternoon is in your future. You cannot turn around and go back any more than you can turn around in time and go back to yesterday. The geometry of space-time inside the event horizon is such that all paths through space and time lead toward the singularity. There is nowhere else to go. General relativity in fact predicts that you would receive a compressed image of the entire future history of the universe outside the black hole as you fell in, because light from all that future time would rush in past you. Whether this actually happens or is cut off by the singularity before you could observe it is an open question that depends on the interior structure of the black hole. How long does that take? For a stellar mass black hole, a few tens of milliseconds to a few hours depending on the size. For a supermassive black hole, billions of times the mass of the Sun, potentially days or even longer, but the endpoint is the same. The singularity at the center is where general relativity breaks down completely. At the singularity, the equations predict infinite density, infinite spacetime curvature. Physics as we know it stops producing sensible answers. Physicists generally treat this as a sign that general relativity is incomplete at that point, rather than as a literal description of infinite density. What actually happens at the singularity is one of the open questions that a theory of quantum gravity would need to answer. Now, spaghettification, tidal forces, are the difference in gravitational pull across an extended object. The side of your body closer to the black hole feels a stronger pull than the side farther away. This difference stretches you lengthwise and compresses you sideways. For stellar mass black holes, which are compressed into a region only a few kilometers across, this tidal stretching is extreme well before you reach the event horizon. The tidal forces at the event horizon of a typical stellar mass black hole would be enough to tear you apart before you crossed. You would be stretched into a thin strand of matter, which is why physicists called this process spaghettification, which is genuinely the technical term. For supermassive black holes, however, the event horizon is so far from the center that the tidal forces there are actually quite mild. The supermassive black hole at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million suns and an event horizon radius of roughly 12 million kilometers. At that scale, the tidal forces at the event horizon are modest enough that, in principle, you could cross it intact and not realize anything special had happened for some time. Finally, there is the information paradox. Hawking radiation, predicted by Stephen Hawking in 1974, arises from quantum mechanics near the event horizon. Quantum mechanics says that pairs of particles and antiparticles spontaneously appear from the vacuum everywhere, normally annihilating immediately. Near the event horizon, one particle of the pair can fall inward while the other escapes. The escaping particle carries away a tiny amount of energy. The black hole loses mass. Over an extraordinarily long time, a black hole should slowly evaporate through this process. But here is the problem. Classical general relativity says nothing can escape a black hole. If Hawking radiation carries energy out, what happens to the information about everything that fell in? Information in quantum mechanics is conserved. It cannot be destroyed, only scrambled. If a black hole evaporates completely and the radiation it emits carries no information about what fell in, quantum mechanics is violated. If the information somehow escapes in the radiation, we need to explain how, which requires physics we do not have. The temperature of the Hawking radiation is inversely proportional to the mass of the black hole. Small black holes are hot, massive ones are extraordinarily cold. The Hawking temperature of a black hole the mass of the Sun would be about 60 billionths of a Kelvin, far colder than the cosmic microwave background radiation that fills the universe. Stellar mass and supermassive black holes are actually absorbing more energy from the cosmic background than they emit as Hawking radiation right now. They will not start evaporating on net until the universe cools below their Hawking temperature, which will take an incomprehensible length of time. The black hole information paradox has been debated since 1974. Several proposed resolutions exist, including the idea that information is encoded on the event horizon, or that it escapes in subtle correlations within the Hawking radiation. In 2019 and 2020, significant progress was made using a technique called the island formula, suggesting that information does eventually escape. The debate is not fully settled. Black holes, then, do something to time that depends entirely on where you are relative to them. From outside, infalling matter appears to freeze at the horizon, redshifting into nothing. From inside, the horizon is invisible and the singularity is inevitable. Time does not stop at a black hole. It does something worse. It stops meaning the same thing for everyone. That is what happens to time near a black hole. The universe, as it turns out, did not design this for your convenience.